Okay, going to be working here on the solutions to 1/6, I believe. Is that what I'm working on today? Let's see. Yes. All right. Number 1. For the function f whose graph is given, state the following. So this is going to require me drawing this for us. Infinity 1. Let's see, at 1 here, let's see, we have a function that goes 1, 2, goes like this. Comes up, comes down, dips back through, goes up, that. And on this side, goes up, let me see, 1, 2, 3. This side it goes up, comes down like this. Then over here, like this. And then, all right, that's my best drawing of it. And they want to know here, part A, the limit as x approaches infinity of f of x. So what is happening as our x value starts to become infinite and go out this way? What does the function do? So the function's, over here doing this, and it dives down. Then when you get past 3, it starts going up. And then what happens is, as you go to infinity, this thing looks like it's starting to flatten out. Now you have to kind of guess that from the picture because it does cut off. But it looks like it's flattening out to a y value of -2. So as you go out, it's asymptotic and it's approaching -2. So this will be -2. For part B, they want to know what happens as you approach negative infinity instead. So this time our x values are going to become negative, and they're going to be negative, and they're going to start getting really big, negative. And so our function is going to start coming out here, and then it looks like it's starting to flatten out again to this asymptote up here at +2. So the y value is approaching +2. For C, limit as x approaches 1 of the function. So notice it doesn't have plus or minus there, so we have to look from both directions. And as we approach 1 here, here's 1. From the left, it's going up to +infinity, and from the right, it's going to +infinity. And since they're the same, positive infinity is the same as positive infinity, we will say that this is going to positive infinity. Now for part D, we want to know what's happening as x approaches 3. Again, there's no plus or minus, so we have to look from both sides. And here's 3. So as we come in from the left, it dives down to -infinity, and from the right, it dives down to -infinity, so it's going to the same place from both sides, so -infinity. All right, now I will let you do number 2 on your own because it looks very similar. And I will jump ahead to number 5. For number 5, we want to draw a graph, sketch a graph that has the following conditions met. So we need the limit as x approaches 2 of our function to go to -infinity. We need the limit as x approaches infinity of our function to become infinite. We want the limit as x approaches -infinity of our function to be approaching 0. We want limit as x approaches 0 from the right, because it has a little plus sign there, of our function to be infinite, positive infinity, and 0 from the left of our function to be approaching negative infinity. And that's it. All right, so let's look at drawing something that does that. All right, so when I approach 2 and it doesn't have plus or minus, that means from both sides I have to be going to negative infinity. So let's say this is 1, this is 2 here. I know my function needs to be approaching negative infinity from both sides. So I'll just kind of draw it down like this. And on this side, draw it down like this. And that should take care of that. Now, as I approach infinity, x approaches infinity, that means I start going out the right-hand side, start drawing this. The function needs to become infinite. So as I go out to the right, it needs to start going up. So I can do something like this. Okay. As I approach negative infinity, that means if I start coming out to the left-hand side, this function needs to be approaching 0. So 0 is the y-axis. So what I'll do is I'll draw like an asymptote out here. I need to be approaching that. Now, I could be approaching from the bottom or from the top. I don't know, it doesn't matter as long as I'm approaching it. So I'll just do it like that. Now, as I approach 0 from the right, I need to be going to positive infinity. So as I approach 0 from the right-hand side, I need to be going to positive infinity. So I need to be going up like this. Okay. And then as I approach 0 from the left-hand side, I need to be approaching negative infinity. So like this. And that's all of the conditions. Now I just need to kind of paste this thing together, make sure it looks like a function. So I can do something like this. Okay. I need to connect these two together, so I'm going to kind of erase that a little bit and make it look a little nicer. That. And then I'll put these two together, something like that. There we go. All right, that function should satisfy all of these conditions. Number 7 is similar enough that I'll let you do that on your own. Okay, now we get to the calculating of these limits by hand. So this is kind of really the nitty-gritty here. This is the good stuff. Number 13. We have the limit as x approaches negative 3 from the right of x plus 2 over x plus 3. So let's try this. First, we'll try a direct substitution. If we do a direct substitution, we're going to replace x with negative 3. Then we're going to get negative 3 plus 2. It's negative 1 on top. And on the bottom, negative 3 plus 3 is 0. And this is a bad situation. However, because we have a fixed number on top, and when we say fixed, we mean non-zero, okay? This is not 0. It's just a fixed number over 0. We already know right now that there's going to be one of 3 possible outcomes. It's going to be infinity, negative infinity, or the limit will not exist. And the way we go about figuring that out is by trying to figure out whether or not this right here is approaching, we know it's approaching 0, but is it approaching 0 through positive numbers or negative numbers? And then also we need to figure out if this is approaching a positive or a negative number. And then from that ratio, we're either going to have positive over positive, positive over negative, negative over positive, or negative over negative. From that, we can determine if it's going to be positive or negative infinity. So it's really just about determining the signs. The only way we'll get does not exist is if we have to come in from 2 different sides, which here we don't, and we get 2 different answers. So let's do this the way I did in class. I'm going to investigate what's happening here on the bottom as x approaches negative 3. So let me draw a number line. Here's negative 3. I'm approaching negative 3 from the right side, so I'm approaching it like this. So what I did in class is I just picked a value here that would be close to negative 3. Now be careful here because of where we are. This is negative 4. This is negative 2. So a number that's really close to negative 3, but on the right-hand side of it is going to be something like negative 2.99, let's say. Now, if I take a number, this number, negative 2.99, and I plug it in up here, negative 2.9 plus 2, that is going to be a negative number. right? It's going to be really close to -1, but it's negative. So I know that what's happening is that on the top, I'm getting a negative number. I'm just put a negative and circle it. I'm getting a negative number on top. And then if I plug in -2.99 into here, -2.99 plus 3 should give me a really small positive number, right? So this is going to be a positive number. And so what we get is a negative divided by a positive, and therefore we must be going to negative infinity. So the answer to this problem is that this equals negative infinity. And we're done. Now, this isn't in the book, but let's just see what would happen if we change this to negative, or to the minus. If we were coming in on the left-hand side of -3 instead, how would it change the answer? Well, we'd start off and we'd still plug in -3 here and here, and we know we would get a form that would look like -1 over 0. This is a fixed over 0, so we know it's one of these answers. And we draw a number line, and this time we're approaching -3 from the right, left-hand side. So I pick a number in here, something like -3.1, and I ask myself what happens. So if I plug -3.1 in here plus 2, that's still going to be a negative number. But now when I plug -3 plus 1, or -3.1 plus 3, that's going to be a negative number. It's going to be small, but it's going to be negative. So I'm going to have a negative down here. And a negative divided by a negative would give me a positive, and so it has to be positive infinity. So the answer here would be positive infinity. All right, let's look at number 16. Limit x goes to pi from the left of cotangent x. Limit x goes to pi from the left of cotangent x. Now we could just go graph cotangent and take a look at it and see what's happening, but we're going to try and do this without graphing it. So what I'll do first is I'll just rewrite cotangent as cotangent is a reciprocal of tangent. Tangent is sine over cosine, so this should be cosine of x over sine x. And now just let's try direct substitution. Plugging in pi for x. Cosine of pi is going to be -1, and sine of pi should be 0. So I know I have a fixed number over 0, so it's going to be one of these three. And now I just need to figure out what's happening. So let me first come over here and put pi. I'm approaching pi from the left. And this is going to be a little bit harder to do because, you know, we could take a number to the left of pi, something close to it, like pi is 3.14, 15, blah, blah, blah. We could do like 3.1. That would be to the left of it. And we could see what happens here, and we could plug it in on our calculator. But I'm going to do it a little different. We know that if you look at the numerator, right? Let's look at cosine. I'm just going to draw its graph. Here's cosine. And if you go to pi, here's 2 pi. Here's the value at pi. It's -1. We already knew that. As we approach pi from the left, the cosine function, we're coming down like this, and we are approaching -1. So it's a negative number, right? It's approaching -1, but the important thing for us to determine this is whether or not this top was positive or negative. In this case, it's going to be negative. Now, for the bottom, sine x, I'm going to draw the graph of sine. Here's 2 pi, here's pi, and we're approaching pi. We know that at pi it's 0, but the question is what's happening as we come in from the left. So I'm up here on pi like this, and I'm up here on the sine function. I'm coming down towards 0, but notice that all these points are above the x-axis, and that means they're all positive numbers. So I know that I have positive numbers on the bottom. So when you take a negative and divide it by a positive, you should get a negative. So this limit right here is negative infinity. All right. I'll erase that. 17. Limit x goes to 2 pi from the left of x cosecant x. limit x goes to 2 pi from the left of x cosecant x. Come on. All right, well, let's rewrite this. This is limit x goes to 2 pi from the left of x times cosecant is 1 over sine. And if I wanted to, I don't have to split it up like that. I can make it into one fraction. So I'm going to go x over sine x. And let me just do the direct substitution right now and see what happens. As x goes to 2 pi, the top goes to 2 pi. That's a fixed number. And then sine of 2 pi is 0. So this is a bad situation. But because it's fixed over 0, I know it's either going to be infinity, negative infinity, or does not exist. So let me try and figure that out. I'm taking my number line. I'm approaching 2 pi from the left-hand side. So let's talk about the numerator. If this is approaching 2 pi, well, 2 pi is a positive number. I know the top is going to be positive, so I'm not really concerned about that. For the bottom, I'm going to need to look at the sine curve. Here it is. And I'm approaching 2 pi, right, from the left, which means I'm on the sine curve down here and I'm coming up towards 0. But all of these are below the x-axis, so these are all negative numbers as I come in, so it's negative. And we get a positive divided by a negative, that's negative. So we know that our answer here should be negative infinity. All right. $19. Limit x goes to infinity of 3x minus 2 over 2x plus 1. All right, so as x goes to infinity here, right, this is the big difference. This is different than the ones we did before. We have a limit at infinity, so we're letting x go to infinity here. What happens? Well, infinity times 3, that's going to be a huge number. We subtract 2, it's going to still be a huge positive number. So the top here is headed towards positive infinity. And the bottom here, 2 times an infinitely large number is going to be huge, plus 1 is still huge. This is infinity over infinity. And this is another one of our bad situations. But this is not like the previous problems where we're going to get like infinity, negative infinity, or does not exist. For this one, we have to do some algebra. We have to do something to help us get this. So the standard technique here is to try and rewrite the problem in a way that your bottom no longer goes to infinity, all right? So what we do is we identify here, because it's a polynomial, we identify the highest power of the denominator, which is 1. And what I'm going to do is I'm going to try and divide this x by x. So if I divide x by x, I'll just get a 1 right here, and then I'll have times 2. So I'm trying to get rid of the part that's blowing up here, the part that's getting infinite. But the only way to divide this by x is for me to come in here and be clever and multiply the top and the bottom by 1 over x. All right, and then what I'll do is I'll distribute the 1 over x through the parentheses. So 1 over x over 1 over x is just 1, so I'm not changing the problem. So long as I promise you that x isn't 0 though, but x is going to infinity, so no worries. When you distribute here to here, you get 3 minus, and then you go here to here, you get 2 over x. And then over, and then you distribute through, you get 2, and then plus 1 over x. And now things are good, because as x goes to infinity, this doesn't change, but 2 over a huge number, right? And we talked about this in class. When you have a fixed number on top and the bottom gets huge, that ratio goes to 0. So this piece right here, when I take the limit, is going to go to 0. And then this 1 over x will also go to 0. And the only thing that'll be left is the 3 over 2. So you'll get 3 halves. All right, let's look at 20. Limit x goes to infinity of 1 minus x squared over x cubed minus x plus 1. All right, well, if I let x go to infinity here, this can become infinity squared. That's huge. 1 minus a huge number is going to be a huge negative number, negative infinity, over, we get infinity cubed minus infinity. Now that's kind of weird, okay, infinity cubed minus infinity. But since this has a higher power than this one, this number should be bigger than this one. So these two together should be a positive number, and it should be infinite because it's going to get bigger. Plus 1, it's still infinite, so the bottom is also going to infinity. So we have infinity over infinity, and remember, I said in class, doesn't matter if this is positive or negative, how it goes is if you have an infinite expression over an infinite expression, you're going to have to do something, some algebra. So I'm going to do the same thing I did in the last one. I'm going to look at the denominator. I'm going to identify the highest power of x here, and I'm going to come in here and I'm going to go 1 over x cubed, 1 over x cubed, and multiply those through. And when I do that, I get limit x goes to infinity. Let's see, here to here we get 1 over x cubed minus here to here, you get here to here, right, this second one, you get x squared over x cubed, and if you reduce that, that's just 1 over x. And then on the bottom, here to here, you get 1 minus here to here, you'll get minus 1 over x squared because you reduce out one of the x's. And then here to here, you get plus 1 over x cubed. And now good things are going to happen. If x goes to infinity, fixed number over infinity goes to 0. Fixed number over infinity goes to 0. So on the top, you have 0 minus 0. This is going to 0 on the top. On the bottom, you have 1 minus. This goes to 0 because you're fixed over infinity. This goes to 0 because you're fixed over infinity. 0, 0, and you have a 1 down there. And hey, 0 divided by 1, that's okay. That's just 0. So this function is approaching 0 as x goes to infinity. Let's look at 23. I really like 22, but I'll do 23. Limit x goes to infinity of 2x squared plus 1 squared over x minus 1 squared times x squared plus x. All right. All right, we start letting x become infinite. This is going to be infinite. Times 2 is still infinite. Plus 1 is still infinite. Squared, infinite. So the top is headed to infinity. The bottom, infinity minus 1, that's infinitely big. Squared, bigger. Infinity, all that, it's infinity. Okay, so we're infinity over infinity. Now in the last two problems, all I did when I had this was I just identified the highest power of x in the denominator, and then I came through and I multiplied top and bottom by that. But here, because these are written this way, I actually have to expand this out first. So let me multiply this out. X minus 1 squared is x minus 2x plus 1. That's what this is. And then times this, x squared plus x. And then I just distribute. So I get x cubed plus x squared, that was this one. Then this one, minus 2x cubed. And this one here, minus 2x squared. And then this times this, plus x. And then this times this, which is going to be, I'm sorry, this one, plus x squared, and then plus x. All right, let me just double check this. X cubed plus x squared, negative 2x cubed, minus 2x squared, x squared. Okay, combine like terms, negative x cubed, and I feel like I'm really missing something. I apologize. Ah, I see what I'm missing. I knew something didn't seem right there. I hope you see it. When I multiplied this out, I should have had x squared minus 2x plus 1. Okay, that's better. Okay, now here times here, x to the fourth, here times here, plus x cubed, here times here, minus 2x cubed, here times here, minus 2x squared, here times here, plus x squared, here times here, plus x. And this is x to the fourth, minus x cubed, and then minus x squared plus x. So that's my denominator. So I'm going to rewrite this. X to the fourth minus x cubed minus x squared plus x. And in the numerator, I actually have to do the same thing. I have to multiply that times itself. And when I do that, I should get 4x to the fourth plus 4x squared plus 1. I'll let you do that yourself. And now I identify the highest power of x that I see in the denominator, which is x to the fourth, and I come in here with a 1 over x to the fourth and a 1 over x to the fourth, and I will pass that through to each of those. So this is kind of a trick that we're doing here. All right, when I pass it through the top, I'll let you do the computation yourself, but you should get 4 plus 4 over x squared plus 1 over x to the fourth all over, and then when I pass it through here, I get 1 minus 1 over x minus 1 over x squared plus 1 over x cubed. So that's what I get when I multiply through. And now when I take the limit, the 4 and the 1 don't change. This goes to 0, this goes to 0, that's 0, that's 0, that's 0. So you just get 4 over 1, which is 4. All right. Let's look at 20. Man, I really don't like that they don't have one. Well, I would just say make sure you pay attention to the examples I did in class, because there are definitely some limits that you might get on your test that are similar to the ones that I did in class. Specifically, if you have a square root in the denominator and how I handled that. I had to like force something into the root. You'll know what I'm talking about once I go through my lecture. All right, 25. So we have limit x goes to infinity of square root of 9x squared plus x minus 3x. All right. Now, in this particular problem, if x goes to infinity, this is infinite times 9, it's still infinite, plus infinity is infinite, square root of infinity is infinite. So this whole thing is infinite. So we have infinity minus 3 times infinity is infinity. Infinity minus infinity, now that's a different case, okay? We've been looking at, up to this point, we've had 0 over 0, we've had fixed over 0, we've had infinity over infinity, and these could be plus or minus, it didn't matter. Now we have this new form, infinity minus infinity, and that's its own little case. You have to deal with this one a little different. So what you need to do is try and turn this into multiplication. All right, that's going to be my goal here, is to try and make this somehow multiplication. I can do the conjugate, and that's because I have a radical. So let me try that technique first. I'm going to multiply this by its conjugate, and that means plus 3x, but I can't just do that out of nowhere. I have to do that over itself. Now there's no guarantee that this is going to work, but this is something I'm going to try. right? So that's a 1, right? And I'll just put this over 1 like that. And let me multiply out the top, see what we get. Limit x goes to infinity. And now when we do this, because it's the conjugate, this times this, the root's basically going to just go away. I'm going to get 9x squared plus x. The middle terms won't matter because they're going to cancel each other out, so I just get the last two terms. It'll be negative 9x squared. Oh, that's really nice. Over 1 times this, so let me just put that there. It's just going to be that conjugate. And now at this point, the 9x squared, negative 9x squared cancel, and we just have x over that. So because I'm on a board, I can shorten up the time here. I can erase that because they're gone. And now if I try and let x go to infinity, I get infinity on top. All right, so I'm going to write down where we are right now. I've got infinity on top, and then if you look at the bottom, this whole thing is infinite. This is infinite. Infinity plus infinity, that's infinity. See, earlier we had infinity minus infinity, and that was a problem, so we tried to deal with it. Now we've basically reduced this problem into an infinity over infinity, which is like the previous problems we've done. But this one is different because it has a root. So I told you pay attention to what I did in class because I wanted you to have a root problem. Well, this one actually is turning out to have a root in it, so I like this problem. I want to try and identify the highest power of x down here, and that's a little confusing because this looks like this is the highest power, x squared. But because you take a square root, it kind of undoes that, and so really the highest power in here is like an x. And so is this one out here. This is x to the first power. So what I'm going to do is I'm going to try and make this right here not be infinite by getting rid of that x. That means I'm going to divide by x. That means I have to come in here with 1 over x on top and 1 over x on bottom. Let me try this. And I'll multiply it times the top, and I'll multiply it through the bottom like that. So we should get some nice stuff on top. When you multiply 1 over x times x, you're just going to get 1. Things are looking nicer already. Over, now this is confusing, 1 over x times this root. I'm going to take care of that in a second. And then 1 over x times 3x, which is plus 3. Now at this point, we're still not there because if you let x go to infinity, this goes to 0, and this becomes infinite. So if you look at just those two pieces, you have 0 times infinity, and that's still something we can't tell what's going on. So what we're going to do is we're going to force this inside the root. And this is what I talk about in class. If you're going to force something into a square root, then as it goes in, it gets squared. So this gets squared on its way in, becomes 1 over x squared. And then I multiply it times whatever was down there. And then I still have plus 3 out here. And then you pass the 1 over x squared through to both of those terms. And I'll have square root of, let's see, this times this, you just get the 9. Then this times this, you just get 1 over x. You still have here plus 3. And I think we're there. Because if we let x go to infinity now, this goes to 0, and you get the square root of 9. But the square root of 9 is 3. 3 plus 3 is 6. So this should just be 1 over 6, 1/6. That's it. Hold on just a second. Hold on, sorry. All right, sorry about that. Believe it or not, that was an important decision that had to be made. All right, marker. All right, so the conjugate worked pretty good on that one. Let's try 26. 26 is just kind of ugly looking because it has these additional letters in here. Okay, let's let x go to infinity. This becomes infinite. Okay, now keep in mind, a and b here are just assumed to be constants, all right? They could be any constants. We have no control over them, so they could be positive or they could be negative. They could even be 0. So if I have infinity squared plus this thing, which is going to become infinite, could be a minus. It doesn't matter because this x squared is going to overwhelm this linear factor. So this should become infinite. And same reasoning here, this should become infinite. So you have a square root of infinity minus the square root of infinity. This looks like it's going to infinity minus infinity. Bad situation. We're going to try and remedy that. And I will come in here with the conjugate. So if I come in here with the conjugate, I'm just changing the signs between them. And I do that on the top and the bottom. Like that. Make this over 1. Then when I multiply out that top, let's see what I get. Limit of x goes to infinity. All right. Root times same root, root goes away. X squared plus ax. Middle terms don't matter. Last ones, this times this. Root goes away, but it's minus because this is a plus and that's a minus. So the root goes away, which leaves me with x squared plus bx, but I'm subtracting, so I need that in parentheses. And then all of that over this ugly thing right here. Root x squared plus ax plus root x squared plus bx. Limit x goes to infinity. And now let's clean up the top. If we distribute the negative through, that's negative and this one becomes negative. And the x squareds cancel. And what you're left with is ax minus bx over all that root stuff. All right, we are still in trouble. We need to somehow determine what this goes to. And if we try and let x go to infinity, we're going to get infinity minus infinity up here, and that means we still don't know what's going on. I'm going to try and get rid of the highest power of x in here, which also happens to be the highest power of x in here. And to do that, I have to divide x squared. But because the thing I put in here has to start on the outside of the root, I'm going to have to put in 1 over x over 1 over x. Now, why is that? I talk about this in class, I'm sure. Because when I force this 1 over x into the root, it's going to get squared, and it'll become the 1 over x squared that I need. So I'm going to use 1 over x. So this times this times this, I will get the limit as x approaches infinity of, let's see, a minus this times this, the x's cancel, b over, now let's see if you can keep up with this. This goes in here and becomes 1 over x squared, and that distributes to each one of those. So this over x squared is 1, this over x squared is a over x, plus now this 1 over x also has to go to this root and then go inside, and so it would become x squared over x squared, which is 1, plus bx over x squared, which is b over x. And now we can let x go to infinity, and things are going to be good. Because this is a fixed number over infinity, that goes to 0. This is a fixed number over infinity, that goes to 0. And so all you're left with is root 1 plus root 1. And root 1 is 1. So this really is 1 plus 1 on the bottom. And the a minus b doesn't change. 1 plus 1 was 2. So you get a minus b over 2. All right, I'm going to have to take a quick break because I got to take care of something. So I will, yep, there it is. I will be back.